Morning all. So today and Wednesday you get to use the techniques that you've now developed to program a computer to learn. Human beings can learn, but we learn much more intelligently than a computer, but very slowly in some respects. The computer learns routine stuff much faster than we can. And so today's lecture is the first one on machine learning, but before that. The minute we do this stuff, you will want to use it. And so on Wednesday, it's your machine learning project. You will classify song lyrics, and you will decide whether songs are hip-hop or country. And I have to apologize because you're going to decide based on lyrics. But the lyrics that are very useful for discrimination between these two classes, whether it's hip-hop or country, are not safe for work. And so we've had to take them all out. So you are going to get a subset of the lyrics that is approved for public consumption. Anyway, people have liked this project. I hope you're going to enjoy it. All right, normal week. Something has changed. Monday office hours. So we have very few Mondays left. There's today. There's next week. A week after and the week. There are 4 Mondays, I think, still to go, including RRR week. Those office hours will no longer be at BIDS. BIDS has been very welcoming, but there's 500 of us, and we show up in full force, especially when assignments are due, and we make a lot of noise. And there's people trying to work, and so we're trying to give them a bit of relief. So Monday office hours are going to be in Echeverry. Echeverry is just next to Soda Hall up on Hearst. So please, today, if you're going to office hours, don't go to BIDS. Go to Echeverry. 3106 Echeverry is a nice big room. It's our room. You can make as much noise as you wish. All right. Do you have any admin questions? Otherwise, we will get going. Anybody? All right. So it's been a while since I saw you, actually. I just want to remind you of the big picture of what you're doing in regression. You are estimating or predicting one variable based on another, and the thing that you're predicting is numerical. And that's not a point that we've belabored, but today it becomes very, very important. We've been predicting a numerical variable, and we've been able to say stuff like, the variable, the predicted age is in the range 21 years to 23 years. We've predicted by intervals, because when the thing you're predicting is a number, there is a concept of an interval, right? It could be any one of several things. But now a question arises, which is, what if the thing that you were trying to predict is not a number? What if it's a category? Then what do you do is the question. And where does this come up? I'll give you a few examples. You have a medical procedure which is trying to diagnose whether a patient has cancer or not. So they will take some, they will draw some cells, they will do some measurements of perhaps what's in the blood, perhaps what's in the cell. And having done those measurements and with past experience, they know that, these people had cancer, and this was what their measurements look like. And these people didn't have cancer, and this is what their measurements look like. Now we have a new person, and we have their measurements. Can we say whether or not they have cancer? So we're not trying to predict, how much of something they have in their blood. We're just trying to answer a yes or no question. We're trying to classify the person into cancer or not. So this problem is called classification. And that is what we're going to be doing this week. We're going to be solving problems of classification. Amazon does that all the time. You have a history with them, perhaps, if you buy stuff. So it's not just what you've bought, but it's what you've searched, and they know all about you. And one decision they have to make is, do they give you a particular ad or not? And they'll feed you an ad if they feel that you're likely to click on it, right? Otherwise, it's a waste of everybody's time to provide that ad. And so based on their experience, they're going to decide whether they should give you something or not. Based on their experience, they have to decide whether the order that you are placing is fraudulent or not. Because some percent of orders are fraudulent. It's somebody's stolen credit card, or it's being delivered to an address it shouldn't be delivered to. And they have some track record of knowing which ones are fraudulent and which ones are not. Based on that, they have to predict so that they can reduce their liability. And, the better they are at predicting what's fraudulent, the lower the prices are for all of us. Because if they have a lot of fraud, they have to pay for that. And, well, who pays for that? The consumers do, right? So there is an issue. And I want to finish my list of examples by a very serious question of classification that has arisen in the United States this past weekend. So there was an election last week, and now people are trying to work out what on earth happened. And one of the questions that has been raised is about social media, Facebook in particular, and their responsibility in disseminating so-called news which is false. And so there's a very serious question here as to the responsibility of the social media. To what extent is the medium responsible for what people are doing? How does freedom of speech come in? But we're not going to go into that. I want to focus on one aspect, which was in Mark Zuckerberg's letter that he posted yesterday, actually. So Facebook has been taken to task for allowing the spread of so-called news articles. There was one apparently that said there was some staffer at the FBI who committed suicide because Clinton was not going to be prosecuted or something, none of that happened. But what happens when machines learn what people click on is that they see what people are clicking on, they realize that something's being clicked on a lot, they send that around more and more and more. And so untruths get sent around. And Facebook was told, you need to do something about this. Now, there's the classification problem of all time. There is a piece of text. Mark Zuckerberg isn't going to read it to decide whether it's true or not. The machine's going to read it. The machine's going to read other pieces of text. And then what is the machine asked to do as a classification problem? Classify as true or false. That is very, very deep. And not only is it very hard, Zuckerberg also raises the issue of who's the arbiter of what's true or false. Nevertheless, this is the current hugely important classification problem that is facing the online world. And so this is serious issues, and what we're going to do is we're going to, on a small scale, see what the factors are that are involved, and we are going to develop simple classifiers that can be used in a surprising variety of settings and that are surprisingly accurate. So that's the goal. And I want to start by introducing you to some language. So the problem is one of classification. Your response variable, the thing that you are trying to predict, is not a number, it's in categories. And we are going to focus on just two categories. The simplest classification problem is called binary classification. The response is an answer to a yes-no question. Right? So is the cell cancerous or not? Is this news story true or not? On a dating website, are these two people going to be compatible or not? They're doing it all the time. They're doing it all the time. And by the way, you guys, let me point out a little piece of machine learning that has occurred at a university that we will not name to do with a university administrative system that is online that sends email to students. We won't name that, but it rhymes with B courses. And it sends a lot of email. especially at the beginning of the term. It sends a lot of email. And there are students whom we won't name who get really annoyed by those emails. And therefore, they flag those emails as spam. Machine learning occurs. And machines learn, oh, emails from this address are spam. Consequence, for the entire campus, they start going into the spam folder. And so the ones that are actually needed also go into the spam folder, and we have to sort of unlearn the learning that has occurred. So, machine learning isn't always the most useful thing. I find it very annoying that when I go to a newspaper site, an online newspaper site, I read something. For the next 3 days, I just keep getting that same thing, right, or some relatives of it. And so whereas I am going to the internet to be exposed to ideas that I wouldn't usually have, to see something new from this bigger world, what they keep feeding me is what I've already read. And this, turning our minds into these silos of only one kind of repeated information does need to be handled. So we're going to do binary classification, and it's on the whole a good thing, but, it can be problematic. Anyway, we're going to do classification. Here we go. So we're going to try and classify the response into one of these categories. This entire slide is just language based on predictor variables. So if you're trying to decide whether some order to Amazon is fraudulent, there are some predictor variables that you might use, such as, for example, is the billing address of the credit card the same as the shipping address of the order? Because if they are different, then perhaps, you want to raise some issues. What is the history of that particular user, et cetera, et cetera, et cetera. Those are what we used to call predictors in this area of data science are called attributes. And then you have to, in order to decide whether something is fraudulent or not, you have to have some past experience. Right? You have to know that in the past, this order had these attributes, and we know it was fraudulent. Or this order had these attributes, and we know that it was not fraudulent. So you have what are called training data where you're confident that you know what the classes are, and now you are going to use that information to figure out, with a new point, whether it's a 0 or a 1. Okay, so I'll pause for a second. This is just language for any questions about the language? Okay. So what I'd like to do now is remind you how we did predictions when we had numerical variables. And long, long ago, the very first prediction we did based on one variable to predict another was a long time ago. We had those Galton's data, and we had the parents' mid-parent height, and we were trying to estimate the child's height. And what did we do there? We said, okay, so here's a new couple, and they have a mid-parent height. How do we estimate their child's height? And what we did was we said, let's go to our original data, find all the couples like these people. Yes? We found all our data that had mid-parent heights around this new couple, and we said, let's look at their kids. And whatever their average height was, that's what we'll project. Do you remember this? Yeah? So we said, take the new people that we've got and find in our old data, in our new language, it'll be our training set, find in our training set people just like them. And then use their results to make a prediction. In our new setting, this is called nearest neighbor classification. And here's what happens. You've got some new individual, and the class is unknown. And just to fix ideas, please remember that the class is either a yes or a no. It's a 0 or a 1. You don't know whether they're a 0 or a 1. So what you do, but what you have is a training set of different people for each of whom you know whether they're a 0 or a 1. So you find the person in the training set who is closest to this person. And, you have to define what close means. But you find the person in the training set who is the closest or looks most closely resembles this new individual. Now, that person in the training set has a class, do they not? Yeah? And you're completely confident what class that was. You just give this new person that class. So you have a new person and you have their nearest neighbor in the training set. The nearest neighbor in the training set, you know, was a 1, say. You say, okay, I'm going to take my new person, I'm just going to call them a 1. So that's in words what is going to happen. I'll take, yes? The question is, what if the new individual is very far away from the training set, and so even the closest person is not close, then it feels inaccurate. You can have that situation, and we will spend some time seeing how accurate or not our classifier is. In general, though, whether it's classification or regression or anything, if your new individual comes along and they're very different from your training group, you should ask yourself why you are using that training group to predict that individual. It's the same thing as we said, supposing you have regression and you have a bunch of ages, and based on the ages you've predicted incomes. Right? And then a new person comes along who's much older than your sample. Do you just extend your straight line until it hits them? Maybe you shouldn't do that. So there is a fundamental question that I think the question that you're asking is not particular to this. It's in general to do with prediction and extrapolation. So I would warn against, in any situation, trying to use a training set to make predictions for somebody who doesn't look like the training set at all. All right, so a lot of talking. This thing just is very, very visual. So we're going to take a look at how this develops. Now, there is a difference between today's lectures and the lectures that you had in the past. Today, what I would like you to do is just focus on the ideas. Some of the code is going to be mysterious. On Wednesday, we will take the ideas that we have. We will develop a way of making a classifier. On Wednesday, we will line by line develop the code for the classifier. But there are a lot of ideas to get straight, and so today I implore you to please don't focus on the code cell, even if you are following along in the textbook, but focus on the ideas. So the text is written that way. All right, so let me see. I think I ran all the cells that I need to run. I'll just do that again. So here is, we're going to work through an example. So here is data on how many people? 158 people. And the question is, these are medical data, and the question is whether they have chronic kidney disease or not. Okay. Now, if you look at the variables, you can see each row corresponds to a patient. There's the age, there's the blood pressure, and there's various quantities to do with what's going on in their blood, etc., etc., etc. You can see lots of variables. Some are categorical, some are quantitative. Do they want to eat? Are their feet swollen, etc., etc., etc.? And then finally, there's a class. For these data, we actually know whether the person has chronic kidney disease, that's a 1, or does not, there's a 0. Okay, why don't we take a look at... There's got to be a 0 at some point. There we go. So these are all the people who don't have chronic kidney disease. Okay? And so here we have a set of people for whom we have a lot of variables that have been measured, and we know whether or not they have this disease. And based on some medical expertise, which I certainly don't have, we believe that these variables are relevant. And now there's the question of how can we use this data? If a new patient comes along, we give them a blood test, right? And we have their age and so on. how can we tell, based on these data, whether they have chronic kidney disease or not? That's a classification question. Everyone agree? So before we get into details of it, I'd just like to take questions on the setting. All right, now there's a ton of variables. We are going to simplify. We are going to use only a few. We are going to use hemoglobin, we're going to use glucose, and we will use white blood cell count. And I want you to take a look at those variables. Hemoglobin, whatever this is measured in, these are numbers like 10, 11, so on. If we take a look at glucose, they're in the hundreds. Yep, whatever units of measurement there are. And then if we look at white blood cell counts, they're in the thousands. Now, we are going to want to know whether points are close to each other. And when you are visually trying to see what is close, it is actually very hard to decide what is close if the scales are different. Right? When you look at a plane and there are 2 points on it, and you're trying to decide whether these 2 points are closer than these 2 points, in your mind, automatically you assume that the scales are the same on both sides. So when you have scales that are vastly different, but you want to compare all of them, what is the scale that you use? Standard units. You standardize. Great. So that is what we are going to do. So what we have done here is we have simply reduced the table. Actually, let me. Quite a bit. So we just have hemoglobin, we have glucose, we have the white blood cell count, and we have the class. And all of these three attributes have been converted to standard units for ease of comparison. Now, what we'd like to do is, we have no idea how these variables work out. So what we'd like to do is we would like to draw a scatter diagram to see relations between the two. But you would love to be able to see in your scatter diagram which ones are the ones and which ones are the zeros, yeah? To see if the variables somehow are connected to the classes at all. So what we're going to do is we're going to color points in the scatter diagram, and I have a little color table. The ones are going to be blue and the zeros are going to be gold. And we will join our table. Don't worry about the code, please. And if you spend some time, you will be able to figure out. What's happened now is that all the zeros have become golds, and all the ones have become blues, and now I will draw a scatter diagram of hemoglobin on the horizontal axis, glucose on the vertical, and there is an option to scatter that says if you specify a colors variable, then each point comes out in that particular color. Ready? So what you're looking for, there's going to be a scatter diagram, and what you're looking for is, can you separate the gold points from the blue points? That's the goal. Yep? All right. How'd you like that? The blue points, notice that at this point we don't care about the shape of the scatter diagram. What we care about is there a separation between the gold ones and the blue ones? What do you think? It looks pretty separated to me. Right? So if you know for the new person their hemoglobin and their glucose, you really ought to be able to tell whether they're a gold point or a blue point. This is a very separated kind of data set. Just pretend you're a doctor. What kind of values of, what kind of test results will lead you to conclude that the person does not have chronic kidney disease? I'll remind you, that does not have are the zeros that are the gold. So talk to your neighbor. You're going to get test results on hemoglobin and glucose. What kind of test results are going to tell you that, I don't think this person has chronic kidney disease? Go ahead. Remember the scale of standard units on both sides. So what kind of values of hemoglobin point to, and I don't think this is chronic kidney disease. Sorry? So positive in standard units, meaning above average values of hemoglobin, right? Then you start thinking, okay, this person, I'm guessing, doesn't have kidney disease. What about glucose? Yeah, average to below average, right? That is what, so it's the lower right. That is, the lower right is the non-kidney disease people. And if I look at glucose, if the level of glucose is quite a bit higher than average, I'm going to predict chronic kidney disease. That's what these data seem to be indicating. Okay? So what we are going to end up with is a new person. The new person is going to be a point somewhere on that scatter, and we are going to figure out whether we think they're blue or gold. So what are we going to do? What does the nearest neighbor classifier tell us we should do? Find the nearest point in this scatter diagram to our new point, and then look at the color of that point. Whatever color that is, that's your prediction. Yep? So what we're going to do is we're actually going to do that. We're going to take a point, and so I have a function called, Alice. I should tell you that David Wagner wrote, there's a link to his Wikipedia page. David Wagner wrote this chapter. He is one of the co-developers of this course, and he has given these lectures both times. He wrote this chapter, and he said, supposing there's a new person called Alice. So I'm sticking with Alice. And I'm going to show you okay. So this blue and gold is exactly what you saw before. Alice is the red point. And what this graph does is it finds the nearest point to Alice and just connects them, just to show you which is the nearest point. Okay. What I'm feeding it are the two coordinates. So Alice has 0 hemoglobin and 1.5 glucose. Just take a look at that and just ask me any questions about that graph, what it is trying to display. Because we're just about to change where Alice is and see what goes on. Okay, so it should be the case, what is this point right here is minus 1, 2. You agree? So minus 1, 2 should be close to one of these blue points. Let me just make sure that that works. Yep, that's the closest point. So it looks like this thing is doing the right thing. You got a point you want me to use? 1 and 0. Okay. So 1, 0. 1 and 0. So if I look at it right here, the point you've given me is on an edge. Yep. And so let's just take a look. Well, that's really, really close to a gold point. Yep. So I'm going to say gold. But the question that you raise is an important one. Why don't we look at a point that's just about here? Let's look at 0, and let's look at 0 and 1.5. Okay, so that's where I started out. That was closest to this one. And now I'm going to drop this point and make it come closer to the gold points. Okay, so 1.3. Aha, it's now closest to this blue point. Okay, so because I'm looking at this distance and this one, and what the computer is telling me is that this one is still smaller. But it sure looks like they're becoming comparable. Yep, so how far do I go? What if it's 1? Still that one. So you can see that these points are large. It looks like it should be here. Okay, so I was fiddling with this. Still? Okay, fine. You can see it's hard to tell by eye, but finally. So first, each point does have a closest point. the program can identify it. And for some points, it's very easy to tell which are the closest points. And for some points, it's harder. And the points where it's harder, the point where your decision could be blue or it could be gold, you're not quite sure, those are points near what is called the decision boundary. And so what we're going to do is, just to make sure that we understand what this decision process is going to be like, we have one Alice, and I've moved her point around, and we have seen whether we're going to predict blue or predict gold. We're going to take 100 Alices, and lots of them. Okay. So what this picture is doing is, first we have our original gold points and blue points. No difference. They are our training set, as we had before. And there's hundreds of Alices. So those red points are unclassified. We don't yet know what their classification is going to be. Now, this cell takes a while to run, so I'm going to run it while I talk. All right. So could you talk among your friends and make some decisions about which red points you can classify just by looking and where you're going to have trouble, please? What about that one there? Easy to classify or hard to classify? Easy to classify. What's your classification going to be? Blue, right? So you're going to say chronic kidney disease. All right, that one. Easy. You're going to predict gold. Yes, there's no blue anywhere in sight. How about right there? Why is that one hard? Because it is being pulled by that blue one and by this gold one about equally. Yeah? And so what happens is, when you start looking at boundaries of these sets, you start, so like here is a point at an edge, here is a point at an edge. If my point is right here, I'm going to go gold. If my point is here, I'm going to go blue, but the center is my boundary. Yep. And so we've had something that's chugged away, and what it is going to do is it's going to color each of these red points, blue or gold, depending on which color is the closest point, and here we go. So take a look at that and talk to your neighbor and see if you agree that that is a reasonable thing to do. You can't judge everything by eye, right? But take some points where you think you might be able to decide and see if it gives you the right thing. So if I just look at this line along here, if my point is here, it's closest to this one. If my point is here, it's closest to this one. Do you see the boundary is almost exactly halfway in between that guy and this guy? If I am here, I'm being pulled by this point and this point. So if I'm here, this one has an effect. If I'm here, that one has an effect. And if I join these two lines, the boundary is halfway in between. And so we have, what you have up here is the decision regions, and you have the decision boundary, and, if your point happens to be here, you have this worry that, I might make a mistake. Yeah, you might. Right. But these data are clean enough that you really feel that if the training set is representative of the overall population, you should be pretty accurate in your prediction. All agreed? Okay. Now, it's not always true that you have this beautiful separation. For example, if we were trying to use glucose still, but now on the horizontal axis, white blood cell count, you feel like you should be able to make a pretty accurate prediction, but there are some blue points among the gold. And there is where you feel that you might mess up. Yep? Okay. So one way to do this, one way to approach this is to just stand here and say, if I get a new point just there, then the closest point is this blue one. But aren't there also rather a lot of gold points around it? So if I just go by the closest point, I might end up concluding blue, but I have ignored the fact that it's sitting in a gold cloud. So in this situation, what we do is we don't necessarily have to use the nearest neighbor. We can use the 5 nearest neighbors. Yep? So we find not just the nearest one, but the ones that are close. And so we could look at the 5 nearest neighbors, see how many of them are gold and how many of them are blue. Now, because we've taken 5, you agree that there's going to be one of them is going to be a majority? It can't be equal? Yes? We can just pick the one that's the majority. That's another way of making this decision. And that is called K nearest neighbor classification. You've got a new individual and they've got an unknown class. You find the K closest individuals in your training data. And those are the K nearest neighbors. Almost invariably, you will have taken K to be an odd number because the prediction that you're about to make is you look at those K nearest neighbors and find the majority. Right? Is the majority blue or is the majority gold? If the majority is blue, you call your new person blue. If the majority is gold, you call your new person gold. And you don't take 4 nearest neighbors because then that way you might have ties and then you won't know what to decide. Okay? So our 1 nearest neighbor is an extreme case of this. Just the nearest one. Typically, you will use a neighborhood. You will use more than one and look at a majority vote. And that is what we will implement on Wednesday. So let me pause for a second and take some questions on what we have so far. Again, as you can see, I'm just showing you pictures, and we're talking through the plan and the motivation for what we're about to execute and implement on Wednesday. Yes? The blue plot inside the yellow cloud would have mostly yellow around it, and so you would end up maybe predicting yellow. However, for a point there, if you were doing 3 nearest neighbors, you would predict blue. You can certainly change your decision process. You can weight something more than something else. Absolutely. We're just going to do the simplest thing first. And in fact, I will show you in just a moment exactly how that comes out if we just do 1 nearest neighbor and then on Wednesday we can do more. Yes? So would there be a limit of how big you make K? Because if you make it very good question. Would there be a limit of how big you make K? There ought to be. Right? So if you make K to be the entire sample size, right, then you will make the same decision. So yes, how to choose K is a very significant question. And that is why you are going to be given a project on Wednesday. And you are going to be figuring out how to choose K. And for this, I really need to talk about accuracy. Right? Which classifier is more accurate than the other? And for this, we actually need to talk about, how do you know whether you're doing well? Okay, so these are my data. And I have to decide whether I can predict correctly or not. So let's just go back to our one nearest neighbor classifier. That's what we're going to use. So a new point comes along. We're going to find the point on this graph that is the closest, and we're going to assign that color to our new point. That's our one nearest neighbor classifier. How do we figure out if that's any good? Talk to your neighbor, please. Think about ways in which you might figure out whether that's any good. How did we figure out whether any estimate was any good? So supposing you're trying to figure out the proportion of smokers in a population, right? You've got your sample and you've got a proportion of smokers, like say 32% were smokers. How did you figure out whether that estimate was any good or not? You sampled again. Yes, to see whether it would have been different had you sampled again. Right? You didn't just stick at 32. And so here, what I'd like you to do is to see, okay, so you have to be able to test your classifier on a new point. Now, if your new point comes along and you say, okay, it's blue, how do you know if it's right? Well, you have to wait until somebody does a medical test and actually decides whether the person, by, looking at their kidneys, whether they have chronic kidney disease. But by that time, it's too late for this person. So that doesn't seem like a very useful thing to do. Right? Because then what's the point of your machine? So we need some people whose data we already know. Whose data do we already know? Well, these people. Yes? So if we see how our classifier does on these particular people, so for this person, say, what is that person's nearest neighbor? This person right here. In our cloud of points, what is that person's nearest neighbor? Ooh. The smallest distance between that person and any point in our scatter diagram is what? The one above it? Okay, so I'm going to look at, so I have to look at every single point on this scatter diagram and find the smallest distance between this point and any point on this scatter diagram. Yep. So you're all looking at this, going, it's that one. Yes? What about this one? Is that not a point on the scatter diagram? Yes. What's the distance between that point and itself? 0. That's the smallest one. So if you just go by the smallest distance, you're going to say, yes, got it right every single time. And you're going to be very pleased with yourself. And you're going to be an idiot. All right? Overly optimistic, thrilled with yourself. So what you've done is you've snooped this data. You've come up with a classifier. And then you're going waving a flag saying, my classifier is the best. Right? It's the Donald Trump of classifiers. No classifier is better than this classifier. Right? This doesn't work. You can't test on your training set. You need a different set, right? And so in order to find that different set, what we are going to do is a version of what we have done when we had numerical data, we did the bootstrap, right? We just sampled over and over again. But some of these data sets can be huge. You can't resample that same size over and over again. And for various other reasons, what we will do is we will simply say, okay, we've got a training set. We will just split it at random. We will take a portion of it to explore and develop a classifier. And then we will try out that classifier and what's left over. Right? And so if we see that what we developed on this portion of our training set actually works pretty well for the rest of it as well, then we have some confidence that, for the entire population, it should work reasonably. So we have now our training set is going to be a subset of this sample, not the whole thing. We're going to set aside some data. We will hold them out. We will take a sample of this. We will develop a classifier based on that. And then we'll see how it does on the bits that we have held out. How am I for time? Okay. So actually, let me skip through. Okay, so here are white blood cells and glucose, and here I am shuffling the whole lot, all the rows of the table, randomly permuting them. I'm going to take some of them for my training group and the remainder for testing. If your original sample is small, you're stuck, right? I mean, your accuracy is going to be an issue. You're going to need data. So I'm going to shuffle. I have 100 and why do I have 79? It must be because I have 158 rows in all. So I shuffle the whole lot, right? And I take the first 79 to train on and the remaining 79 to test on. Okay. And so if I take, this was my original picture, if I just look at the scatter of my training set, okay, so this is some randomly selected group, and you can see that there are some blue points among the gold, but not as many as before. Yes, that was the whole thing, and now you have this. So we develop a classifier based on this, and this is the one that takes a little time. So we develop a classifier based on this, and then what we're going to do is we've got our testing set, which is held out, and we will place those points on our little blue and gold grid and see how we do. And are we chugging? Ooh, I think we're done. That's the classification region that we get. So let me just see, shall we just see if it makes sense? So we go back and look, this was our particular training subsample that we got, right? So it's got some gold stuff, but it's got a bit of blue up top, right? And so what we are saying is that for most points out here, we'll predict blue. For most points here, we'll predict gold, but there will be a little bit of blue up top in the predictions. That's our classifier, right? So this is a picture of our classifier. You give me a point, that's the classification that I'm going to make. And what we're going to do now is we're going to overlay which set? The test set on this and see how we did. There you go. What do you think of the accuracy? It's okay. The gold points we're really good at. Yes? And the blue points, where do we mess up? This is a mess right here. Right? The thing is actually blue, but we are predicting gold. And there's no surprise that those are the points where we're going to mess up because there are some blue points among a lot of gold. And that was, I think you were pointing out that, aren't you going to always be predicting gold there? Yes, exactly. So you will have a little accuracy issue, but even so, the simplest classifier, one nearest neighbor, isn't bad. And that is something for us to keep in mind. So you think now if you get a new point, the new point should be like one of these held out points. So overall, maybe we should have a decent fraction of times we get it right. That's the goal. Okay, so I am going to stop here because today I have a human alarm clock known as Sam who has something to say to you.
All right, quick announcement, and then you guys can head out. I'm Sam, one of the TAs for this class. We've just finished Project 2, and as you may now be more aware, it is now possible to convince you, with the skills you learn in this class, it's possible to convince people of just about anything you want. And so we asked the question, how can we use what we learn in data science and the skills of working with data to inform and benefit society rather than mislead and harm people? And to answer these questions, I and some other people from my club are putting together a panel on data science for social good. And it's taking place Wednesday at 6:30 p.m. on Bancroft Avenue. I'm going to be sending out a Piazza post with more details, but I just wanted to make sure you guys are aware of the time so you guys can save it on your calendars if you're interested. Thanks.
All right. I'll see you Wednesday. Thanks for doing that, Sam.